I've been talking about the L'Hopital's rule, and I have a few variations to discuss on that topic. But here's just a sort of a quick refresher here. If I'm trying to do something like, how about, this is a classic L'Hopital's rule problem. The limit as x goes to 0 of sine of x over x. L'Hopital's rule is all about just finding limits of things. It actually, like on its surface, is not about the derivative or the antiderivative, although in order to do it, you use the derivative. This limit, of course, if you're trying to do this limit, you would just try to plug the number in. That is the number, you would plug this x equals 0 in here and see what happens. And when you do that, you get, in this example, sine of 0 over 0, which of course is 0 over 0. This we call an indeterminate form. 0 over 0 is not a number because you're not allowed to divide by 0. But it doesn't even indicate anything like infinity. Or when you see 0 over 0, your impression should be, this really gives you no clue as to what the true value of the limit is. It could be that the limit is 0, or it could be that it's infinity, or it could be just like some other ordinary number. Anyway, when you see 0 over 0, that means you can use L'Hopital's rule. So this is El Hospital, L'Hopital's rule. And the way you do it is you just take the derivative on the top and the bottom. So you get lim x goes to 0. Taking the derivative on the top, derivative of sine is cosine, and on the bottom is 1. And so this, if you want to simplify a little bit, this is just cosine of x. And now I can plug in the x equals 0, and I get cosine of 0, which is 1, and that's the answer. So in this case, this 0 over 0, actually the answer ended up being 1. When you see 0 over 0, the moral of the story is this really doesn't tell you what the answer is at all. You have to do some other stuff, which in this case is the L'Hopital's rule. Any questions about that one? This is like the classic example of a L'Hopital rule, sine of x over x. All right, let's try a slightly fancier one, and then we'll talk about sort of yet more slightly fancier ones. How about tan x minus x over x cubed? All right. This one, we're going to do the same business. So you should not just immediately use L'Hopital's rule. You have to make sure that you really do get 0 over 0, because if you don't get 0 over 0, then actually the L'Hopital rule is not even correct. Like, it'll give you wrong answers. So you should begin by plugging in and see what happens. In this case, I get tan 0 minus 0 over 0 cubed. Anybody recall what is tan 0? You could think of that as sine over cosine if you like. Yeah? It is 0. Yeah, tan of 0 would be sine 0 over cosine 0, and sine of 0 is 0. Cosine of 0 is 1. So, tan of 0 is 0. So this is 0 minus 0 over 0. This is 0 over 0, which means, yes, indeed, we can use the L'Hopital's rule. So we should do that. Now, the L'Hopital rule involves doing the derivatives on the top and on the bottom. I don't know if this is not like a standard derivative that we use every day, but I will refresh your memory. The derivative of tan, anybody actually remember this one? Derivative of the tangent? Yeah? It is secant squared, of x, where secant, of course, is 1 over cosine. So this you could also write as 1 over cosine of x, the whole thing squared. Okay, so that's what I'm going to get when I take the derivative. So this, doing the L'Hopital rule becomes, all right, I still need to write lim. Eventually, I'm going to plug that x equals 0 in again. But the tan becomes secant squared minus x. That becomes a 1 because the derivative of x is 1. And on the bottom, x cubed, the derivative of that is 3x squared. All right. Excellent. And now we should try again to plug this value in. So I am going to try now to plug in 0 over 0. This says secant squared 0 minus 1 divided by 3 times 0 squared, right? And what is all of that? Can anyone say what is secant squared of 0? Remember, secant squared is 1 over cosine squared, right? Yeah?
1.
It is 1, yeah. Secant squared of 0 is 1 because cosine of 0 is 1, and secant is 1 over cosine. So that is 1 minus 1 over 0, right? 3 times 0 squared. So this is 0 over 0. Again, we get 0 over 0. Anyone remember what to do in this case? This, of course, is not our final answer. I mean, we got 0 over 0 to begin with. You may be concerned that this is just like not getting anywhere because we did this and we got the same thing.
Do it again.
Do it again, she says. Yeah, it's you might feel like you're not getting anywhere, but at least like this thing is different from that thing. So at least something happened, and maybe something will continue to happen if we continue to do this again. So I'm going to do the L'Hopital rule again. When you see 0 over 0 again, I'm going to do L'Hopital's rule again. All right? And hopefully it'll work again this time. I mean, it's not exactly the same here. If you took the derivatives and you got exactly the same thing again there, then you're not getting anywhere. But I feel like we might be getting somewhere. In order to do this, we're going to have to take the derivative of secant squared. Maybe we could just like work that out on the side here. Anybody want to suggest a strategy? How do we do derivative of secant squared of x? Yeah?
Put secant squared in terms of cosine.
Okay. So this you could say is the same as cosine. So secant is 1 over cosine. So this is like 1 over cosine of x squared, like that. You could write it this way. And then from here you could do the quotient rule, I suppose, because that looks like a fraction. Although, because it's a 1 on top, maybe the most convenient way to do this would be to write it as cosine of x to the negative 2, and then take the derivative of that using the chain rule. To me, that's a little easier than doing the quotient rule, although you could do either way. So I'm going to do the chain rule on this thing. That means the exponent first comes down to the front, negative 2 in the front, cosine x to the minus 3, because you are decreasing the power by 1 when you take the derivative. And then I go times the derivative of the inside. The derivative of the inside is negative sine x, right? Something like that. Maybe I'll just simplify this a little bit because I'm going to have to be plugging this into some other stuff. The minus signs cancel. 2 sine x, come on now, 2 sine x cosine x to the minus 3. I think that'll do it. All right, so when we go back, this was all kind of a sidebar. When I do the L'Hopital rule here, the derivative of this secant squared is going to be that stuff. All right, let's do it. So here then, doing my L'Hopital's rule again. Hopefully this will get somewhere. 2 sine of x cosine x to the negative 3. Okay, the minus 1 goes away because I'm taking the derivative, and that's a constant. And then on the bottom, 6x. All right. And we're going to try to plug in again and see what happens. Maybe I don't like the negative exponent. I'm just going to rewrite this a little bit. And the 2 and the 6 I can simplify a little. Sometimes you want to kind of clean things up as you go here. I have a 1/3. That used to be 2 on top and a 6 on the bottom, but you can simplify that slightly. Anyway, sine x I'm going to leave on the top. And then on the bottom, x and cosine x cubed. Right? That's just rearranging things a little bit so that it looks a little nicer. Anyway, plug in the value. Plugging in x going to 0. I get 1/3 sine of 0, 0 times cosine 0 cubed. And what does that give me? We have 1/3 out front. Sine of 0 on top is 0. 0 times, cosine of 0 is 1. This is 0 times 1 cubed. That, my friends, is again 0 over 0. Anybody feeling good about this one? Let's do it one more time. This is the worst L'Hopital rule example ever. It turns out you have to do it 3 times and then it actually works. So it can happen that you have to just do it, keep doing it till you're satisfied. Squeeze gats till your clips is empty, as they say. That's a Biggie Smalls. All right, right here. So this is the part before plugging in gave me 0 over 0 again. So I am going to do one last time, hopefully, doing the L'Hopital rule again from here. This time we are going to have to use the quotient rule, so I hope everybody remembers the quotient rule. And it's going to be kind of particularly nasty because the bottom is a fairly complicated thing here, but let's do it. So we are going to do one more time. One more time. I meant to write more. One more time. All right, maybe I'll just, sorry, my writing is a little convoluted at this point. From here, I'm going to do the L'Hopital rule one more time. So I have still the 1/3 will just stay like it is. And we make a fraction where you do the derivative on the top and the derivative on the bottom. Did I say we have to use the quotient rule? I should not have said that. We are not taking the derivative of this fraction. We're taking the derivative of the top and also taking the derivative of the bottom. So there is no quotient involved. There's a product rule on the bottom, though, which is a little nasty. Anyway, up top, we get cosine x, because that's the derivative of sine x. And on the bottom, we have a product. And so you have to use the product rule. It's x times cosine of x cubed. So the first thing is x. I'm going to go the first times the derivative of the second plus the second thing times the derivative of the first thing. X times the derivative of cosine x cubed will be 3 cosine x squared times negative sine x. That was the chain rule on that cosine x cubed. This is only the first part of the product rule. That was the first thing, x times the derivative of the second part. And now I go plus, to finish the product rule, plus the second part like it is, cosine x cubed, times derivative of x, which is 1. So it's like that. This is one big fraction here. All right. I actually feel good about this. This is an especially nasty one, but I can tell at least right away that when I plug in the x this time, I'm going to get 1 on top. So it's definitely not 0 over 0 again, which I like. That means this is going to be the end. So when I finally plug in, I get, okay, 1/3, of course, cosine of 0 up top, which is 1. So this is not going to require another 0 over 0 business. And then we plug in 0 everywhere on the bottom and see what happens. I get 0 times 3 cosine 0 squared times negative sine 0 plus cosine 0 cubed times 1. And what do all of these things? So cosine of 0 is 1, sine of 0 is 0. So all of this business gives me 1/3 out front, 1 on top of the fraction, and then this is 0 times 3 times 1 squared times negative 0 plus 1 cubed times 1. I think all of that big fraction is just 1 over 1. Make sure you're doing your order of operations correctly. All of this stuff multiplies together, and that's 0. And then you add it with a 1. So this is all just 1/3. The big fraction is just 1 over 1. And that's my final answer. All right, we finally ended up with a real number answer here. Any thoughts about that one? This is probably the most involved L'Hopital rule problem you would ever likely come across. You got to do it several times sometimes. All right, great. This is not all that we have to say about the L'Hopital rule. Sometimes you got to work it out a little bit differently. So all the ones that we have done so far, so let me just reiterate here. I have some for you all to try also, but I want to talk about this one variation first. So these all have been indeterminate forms if you look in our book, these are referred to as indeterminate forms of type 0 over 0, right? There are actually other kinds of indeterminate forms that you may encounter when you're doing limits. So, indeterminate forms of type 0 over 0. There are other kinds of things that can happen. So we may also encounter something like infinity over infinity. This also must be considered as an indeterminate form. So if you ever are plugging values in and you end up with infinity over infinity, it's not like the infinities cancel and you get a 1 or anything like that. This is also an indeterminate form which must be handled using special techniques, and in particular the L'Hopital's rule is how we're going to basically always do that. And there are other kinds of indeterminate forms, infinity over infinity or sometimes 0 times infinity. Again, that is indeterminate. You might, from one point of view, you might say, well, anything times 0 is 0, and that's true of ordinary numbers, but there's special rules when infinity is concerned, and you might also consider infinity times anything is always infinity, but anyway, this is also an indeterminate form. All of these things, we can use L'Hopital's rule for all of them. We can use the L'Hopital's rule for all of them. So infinity over infinity, we can just use directly. So I'll just say, do it as usual for 0 over 0 or infinity over infinity. As usual, I mean you take the derivative on the top and on the bottom. If it says 0 times infinity, I'll write this as a separate line here. For 0 times infinity, rearrange it to force it into a fraction. Because the whole point of the L'Hopital's rule is you look at a fraction and you take the derivative on the top and on the bottom. Now, if you instead see something that looks like 0 times infinity, then there is no top or bottom, and it's not obvious what you're supposed to do with that. But my advice is rearrange it to force it into a fraction, and then you do the ordinary L'Hopital's rule by taking the derivative on the top and on the bottom. All right, we'll do some examples. You'll see what I mean. This is not nothing too mysterious here. All right, let's just do a very straightforward one first. For example, what about lim x goes to infinity of x times e to the x? Sorry, that's not what I meant. I meant e to the x divided by x. X times e to the x is not interesting. That's just like infinity times infinity. Okay, e to the x over x, x going to infinity. So the way you begin this is by sort of trying to plug in the value, and this is a little weird because we don't typically think of plugging infinity into things, but if I were to just directly sort of plug in the value, it would look like that. This is not the kind of thing that you want to be like writing or saying in public if you're in the club. Don't go around talking about e to the infinity. This is like a red flag when I meet someone in the club. There's no such thing as e to the infinity. But what I mean by that is I am imagining if I start with a really big number and do e to some really big number power. And what is if I had a really big number and I go e to some really big number? The answer will also be like infinity again. All right, so this is basically the same as infinity over infinity. That's because if you plug a really big number inside the e, you get another really big number. All right. All of this, maybe I'll put this sort of in a red box, meaning I'll put these like scare quotes around it. That stuff in there that I'm writing is not actually specifically mathematically meaningful. This is all kind of sort of an analogy. I'm imagining plugging very large numbers in here. And so when I say infinity over infinity, all I mean is just if x goes to infinity here, the top gets really big and the bottom also gets really big. All right. Anyway, this is an indeterminate form of the format infinity over infinity. And when you see this, it means, Well, this infinity over infinity means we may use L'Hopital's rule, just like as if it was a 0 over 0. So you can take the derivative on the top and also take the derivative on the bottom. And what do we get back here? So doing the L'Hopital's rule, it becomes, anybody remember what's the derivative of the e to the x on top? It is e to the x, yeah. And on the bottom, the derivative of x is 1. All right, so this is lim, just simplifying a little, lim x goes to infinity of e to the x. And what is that? This is infinity, or you could say the limit does not exist. Because when the exponent of e to the x gets really big, the answer here just gets really big. All right, so you could say this equals infinity, if you like, or you could say that the limit does not exist. However you want to say that. All right. The L'Hopital rule is necessary, though. You cannot just look at this at the beginning and conclude that the limit does not exist. Really, you get infinity over infinity, which is indeterminate. In order to figure out what the true answer is, you have to go through this L'Hopital rule step. All right? This is a little more, it's not really harder, I would say, but it's a little weirder with the infinities in there. All right? Great. Let's try some that you have to play around with a little bit. So how about lim x goes to 0 of x times the natural log of x? All right. Now this is one in which you are going to get one of the sort of other weirder indeterminate forms which you have to change into a fraction. It doesn't look like a fraction here at all. But when I try to plug these values in, plugging in, I will get 0 times natural log of 0, right? And we have to think about what is our interpretation of ln 0. Everybody knows you straight up can't do the natural log of 0. Like there is no such thing as ln of 0. If you try this on your calculator, you will get, you'll get some kind of error. But the reason for that is because, remember the way that the graph of the natural log looks? It looks like this, right? This is the graph of ln x. And so when I see ln of 0 along this graph, really that represents something which is negative infinity. If you have x values which are very close to 0, their y values are super big but negative, right? Way down there. So this actually should be interpreted as 0 times negative infinity. And that is an indeterminate form. It's not equal to 0 because the second part is infinite, and it's not equal to infinity because the first part is 0. So this right here, this is indeterminate. So we intend to use L'Hopital's rule on this, but in order to use the L'Hopital's rule, it has to look like a fraction. And this is what I was saying before. We want to force it to look like a fraction. All right, so you start with this, x times ln of x, and I want to write it as a fraction rather than just x times ln x. Anybody got an idea? How could I force this to look like a fraction? I can think of two ways that you could do this. One is a little better than the other, but any ideas? Yeah?
Do you
Take the derivative? I'm not going to take the derivative just yet. Maybe you're thinking, because if you take the derivative, then this ln x turns into 1 over x. Yeah, that's true. Although you have to write this exactly as a fraction. By like simplifying it in a weird way, not taking the derivative or anything. Yeah?
Would you do x to the negative 1?
X to the negative 1 in the denominator. Yeah, this is a great idea. So this is similar to like if I have something like a over b, of course, you can write it as a times b to the minus 1, right? But you can also go the other way around. You can start with multiplication and make it into a fraction like this. So I'm going to actually, I was going to write this slightly differently. This is equivalent to what she said, and you can write what she said if you like. I'm going to write it as ln x divided by 1 over x. She said ln x divided by x to the negative 1 power, which is totally the same thing. And actually, that may be a more convenient way to write it. So this is a weird step. Ordinarily, you would not want to do this because, like, to me, x times ln x is better, is a more simple way of writing this. But for the sake of using L'Hopital's rule, you must write it as a fraction. And so this is the appropriate way to sort of force this thing to look like a fraction, even though it didn't before. All right? But anyway, now that this does look like a fraction, we can use the L'Hopital's rule on this, because here you will notice if you try to plug in ln x, when x goes to 0, that's negative infinity for the same reasons that we said before. And on the bottom, x to the minus 1, when x goes to 0, that is also infinity. And so we now have an indeterminate form that looks like infinity over infinity. And so we may use the classic L'Hopital's rule on this. And this is the purpose of doing that. This admittedly weird step here is to turn it into something that looks like a more typical L'Hopital's rule. All right. So we may now do the L'Hopital rule. We get, I'm going to take the derivative on the top and on the bottom. On the top we have ln x. The derivative of that is 1 over x. And on the bottom we have x to the minus 1. We do the usual power rule for that. It becomes negative x to the negative 2. Right? And now I intend to plug x to x becoming 0 again, but maybe we should simplify this a little bit. I have lots of like fractions inside of fractions here. This, of course, is, I don't know, however you like to simplify weird fractions like this. I have 1 over x on the top, and then down here I have negative 1 over x squared. And so if you sort of flip everything over, this is actually, maybe I'll write it instead as multiplying the reciprocal. I don't know. This is the same as 1 over x, times negative x squared, isn't it? If you flip the fractions over in this sort of whatever, there's a few ways you could think through about re-simplifying this thing. Anyway, what is that? All of that is just negative x, right? After simplifying everything. And now you can just plug it straight in. You don't need another L'Hopital rule or anything. You just plug in x equals 0. The answer is 0. Negative 0 if you like. All right? No funny business at the end. So we rewrote it into a format which forces it to look like a fraction, and then did some somewhat weird but ordinary kind of simplifying so that you could plug it in at the end. All right, I got one more, and then I have some for you all to try out. Here is, how about this here? This is a one-sided limit. Can you believe it? It'll be fine. Tan x minus secant x. All right? This one actually is another type of indeterminate form. This is not a fraction or a product. It looks totally different. But tan x minus secant of x. It might be helpful to try and do this limit. You should probably, and this is not something I expect you to have memorized, but it may be helpful to think about what the graph of tan and secant look like. Tan looks like this. It has these sort of recurring asymptotes. Here's this asymptote is at pi over 2. So when I take this limit of the tan x part as x approaches pi over 2 from the left, that means this way. That first part, this tan x, becomes infinity because as x approaches pi over 2, the y values there go up forever. All right. So this, when it comes to plugging in, that's infinity. What about secant of x? So this one, probably nobody remembers the graph of secant, but I will refresh your memory. The graph of secant has an asymptote at pi over 2 also, and it looks like this. Secant is 1 over cosine, and cosine is 0 at pi over 2 and negative pi over 2. So this is tan, this is secant. I don't expect for you to remember those graphs. If you were trying to do this problem on the homework or something, you should look up the graphs. Anyway, what does the secant give me when I take this limit as x approaches pi over 2 from the left? That means approaching here from this side. Again, we get infinity here. So this looks like infinity minus infinity. And again, this is an indeterminate form. You don't subtract infinity minus infinity equals 0 because sort of you don't really know which one of them is bigger. So this is also indeterminate. And again, we must write this as a fraction. You have to force this to look like a fraction so that you can use the L'Hopital's rule. Anybody have a suggestion here? How can we make these things look like a fraction? We're going to have to use another sort of simplifying trick, perhaps. Surely you all know there is a way to write a tan as a fraction. Anyone know what I'm referring to? Yeah? Yeah, the tan is sine over cosine, and the secant, by the same in the same vein, is 1 over cosine, right? Those are fractions. So I am going to, you must make fractions here. Because I intend to do the L'Hopital rule, and the L'Hopital rule is always, you take the derivative on the top and the bottom. So it has to look like fractions in order to do this. So this, when I make fractions out of it, it's going to say lim x goes to pi over 2 from the left side. Tan is sine over cosine. And secant is 1 over cosine. All right? I still don't like the subtraction here. If you want to do L'Hopital's rule, it has to be just one fraction. And so, but these are two fractions with the same denominator, and so we can actually just subtract them. All right, so this actually, subtract the fractions. They already have a common denominator, so I just get sine of x minus 1 up top, cosine of x on the bottom. And now this looks much more ordinary, and we can try to do the L'Hopital rule here. What happens if we just plug in pi over 2 here? Plugging in x equals pi over 2. It says sine pi over 2 minus 1 divided by cosine pi over 2. Sine of pi over 2 is 1. So this is 1 minus 1 on top. That's 0 over 0. Which I like for using L'Hopital's rule, all right? Since we got 0 over 0, it means we may use the L'Hopital rule. So from here, I am going to do my L'Hopital's rule. I still have this lim. Actually, at this point, the fact that this is a limit from the left side is not really going to be relevant anymore, although we might as well still write it there. Taking the derivative on the top. Can anyone tell me what's the derivative on the top? Yeah?
Cosine x.
Just cosine x, right? The minus 1 goes away. And on the bottom, what do you say?
Minus sine x.
Negative sine x. Excellent. Great. All right. Now we try to plug it in again. Hopefully we don't have to do the L'Hopital rule again. Plugging in this time gives me cosine pi over 2 divided by negative sine pi over 2. And cosine pi over 2 is 0. Sine pi over 2 is 1. So this is just 0. And that's the answer. I get 0. All right. This is how we do it. We got a few minutes remaining. No, 13 minutes remaining. I think that's enough time for you all to try some. Agree? All right, let's try some. Sorry to rattle on for so long. So I have several of, increasing complexity, I suppose. I got 4 here. See how you like it. All right, see what you think. Feel free to chat with your friends. Okay so far?
Just as about stuff.
Yeah.
Got 4. Here. Okay. Yeah, yeah. Okay. Okay. And you have 0 on the bottom. Yeah, you can see.
I'm looking at
Still good here? Yeah, what do you see?
That's considered Texas.
Yeah, right. Still good here?
Yeah.
That's good.
you get infinity over infinity, then you do the L'Hopital again. You get 6 over 2.
Yeah.
It's still not infinity. There's no x to the limit. Yeah. So that's the answer. Yeah. First step though. Still good here? Yeah, this actually is, this you can think is 0.
Okay.
And this also is 0. E to the negative. Because if you put a big number here, to the negative 1 is the same as 1 over e to the negative, which is like,
Okay. But it's still infinity, right?
yeah,
Okay.
but it's like 0.
Oh, gotcha.
Which is what you want.
Yeah.
Still good here? You got 3 here. Yeah, great.
Infinity times 0.
Right. Yeah, so you should rewrite that to look like a fraction. Still good here? Mm-hmm. I think so. Yeah, your answer should never have an infinity.
Oh, so this is actually.
This isn't really wrong, although 1 over infinity is, well, I'm about to do it.
Let's talk these through. It looks like people did great. I think pretty much everybody got 4 for the first one, which is correct. You should try to plug in. You get 0 over 0. And then you do the L'Hopital rule, and it becomes 2x divided by 1. Plug in the x equals 2, and you get 4. So that's everybody got. And I think pretty much everybody got this one, too. This one, if you plug in to begin with, you're going to get 0 over 0. So it becomes the... doing the L'Hopital rule gives you negative sine x over cosine x. And then when you plug this in, you get negative 1 over 0. 1 over 0, your interpretation of that is the limit does not exist. Or you could say this is infinity, or it's not actually in this case. But yeah, this one I would just say does not exist. The limit is undefined because some constant over 0 means the limit does not exist. The next one is a pretty straightforward. It is x going to infinity, but when you plug in here, you get infinity over infinity, so you should do L'Hopital's rule. You get, again, x going to infinity. 6x on top, 2x plus 5. Again, if you try to plug in here, you get infinity over infinity again, and so you do the L'Hopital rule again. This will be the last part. I mean, the last time. 6 over 2. And now some people are a little worried that there are no x's left at this point, but that's sort of a good thing. I mean, this is saying you take the limit as x goes to infinity of this constant. The answer is just going to be this number. There are no x's left over, and so the answer is just 3. 6 divided by 2, which is 3. All right? I think everybody got that one. And then the last one is, I suppose, very slightly complicated. This is one of those ones where you have to force it to look like a fraction. If you just try to take the limit as is, of course, x becomes infinity. E to the negative x becomes 0. That's because I'm looking at e to the negative infinity. If you remember the graph of e to the x, overall, it looks like this, where if x is going to positive infinity, this goes up forever, but if x is going to negative infinity, this goes to 0. So that's why this e to the negative x is 0. So this is an indeterminate of the type infinity times 0. We should rewrite this as a fraction, and pretty much everybody I saw who got this far wrote it like that. And this is the appropriate way to write this as a fraction. Actually, it would work. You could also do e to the minus x divided by 1 over x, although that's just more complicated. This is the simpler way to do it. Anyway, when you plug in here, you get the indeterminate form infinity over infinity, and so we can do the L'Hopital's rule, and it turns into 1 over e to the x. That's the derivative on the top and on the bottom. And then plugging in the infinity gives me 1 over 0. No. 1 over infinity, right? And what's your interpretation of 1 over infinity? This is like 1 divided by some kind of super big number. It is 0. Yeah, when you see this 1 over infinity, that's not your answer. Like, your answer should not have an infinity in it. What this means is you have 1 divided by some super big number as the denominator approaches infinity. This is 0. All right? That's my answer. All right. I think that'll do for today. Thank you for, I do apologize again for being a little scarce these days, but it's all over. Tomorrow's the end of this big process for us. Let me know if you want to talk about the homework. I'm going to be hanging around in my office for the next hour. I would be happy to chat with anybody.